The world's most powerful AI chip isn't being stopped by software bugs or trade wars, it's being stopped by the laws of physics. For decades, the march of Moore's law was cooled by a simple medium: air. Data centers were designed as vast, refrigerated wind tunnels. But a new and unyielding barrier has emerged in the race for artificial intelligence dominance. It is heat. Specifically, it is thermal density, the sheer concentration of heat generated in an impossibly small space. The problem lies in the properties of air itself. Air has a low specific heat capacity, meaning it takes a tremendous volume of it, moving at high speed, to transport thermal energy. Water, by comparison, can absorb over 3,000 times more heat per unit of volume. This physical reality has defined the limits of data center design for a generation. When 72 of NVIDIA's Blackwell GPUs are packed into a single NVL72 rack, the thermal output reaches an unprecedented 132 kilowatts. That's enough energy to power more than a dozen homes, all concentrated into the volume of a large refrigerator. Traditional air cooling was architected around a thermal ceiling of roughly 50 kilowatts per rack. The Blackwell NVL72 obliterates this limit by a factor of nearly 3. To force more air through the system, you must spin the fans faster, but the fan laws are unforgiving. The power required is proportional to the cube of its speed. Doubling the fan speed increases power consumption eightfold. The returns diminish rapidly, while energy cost and noise skyrocket. This is the death of the fan as a primary cooling solution for high-performance computing. Even with infinite fan power, another barrier emerges: pressure drop. The heat sinks inside these servers are dense stacks of metal fins. At a certain point, the air simply can't be forced through fast enough. A stagnant, insulating boundary layer of hot air forms on the chip's surface, and the chip chokes on its own heat. Without a way to remove 132 kilowatts from that cabinet, the system cannot run at its full potential. Overheating forces automatic slowdowns, a process known as thermal throttling. The chip reduces its clock speed to generate less heat, sacrificing performance to prevent self-destruction. The promised speed of the AI revolution runs headfirst into a thermal wall. The conclusion is inescapable. Air is no longer a viable cooling medium at these densities. The industry has reached a thermal tipping point. Direct-to-chip liquid cooling is now mandatory. This is a story of physical limits and how confronting them demands a new foundation for the entire AI infrastructure. To unlock the future of artificial intelligence, the industry must first solve a plumbing problem. Chapter 1. The Thermal Tipping Point. The world's most powerful AI chip isn't being stopped by software bugs or trade wars. It's being stopped by the laws of physics. If you think water is the solution, you haven't seen the math of a 120 kilowatt rack failure. The promise of liquid cooling was immense. A direct, efficient path to carry away the unprecedented heat of next-generation AI. But in the race to deploy, that promise collided with the unforgiving realities of fluid dynamics and material science. In March 2026, the quiet warnings from engineers escalated into a full-blown crisis. The first wave direct-to-chip systems, rushed to market to support the groundbreaking Blackwell architecture, were failing in the field. The initial reports were a trickle, then a flood. The symptoms were varied, but they all pointed to a systemic breakdown. First, persistent overheating. Then came insidious software bugs in the cooling control systems, causing oscillations that triggered false alarms and brought entire racks offline. But the most catastrophic failure mode was also the simplest: leaks. The custom manifolds for the 72 GPU NVL72 racks were marvels of density, but they also concentrated hundreds of potential failure points. Every joint, every seal, every quick disconnect fitting became a liability. Inside these systems, high pressure and relentless thermal cycling, the constant expansion and contraction from heating and cooling, stressed materials beyond their designed limits. Gaskets experienced seal creep. Microfractures formed in polymer components. One drip of conductive coolant is all it takes. A single drop on a high-power circuit board can destroy a multi-thousand-dollar GPU node, and worse, trigger a cascading shutdown of an entire rack. The physics of failure had migrated from the silicon chip to the plumbing. At the center of this crisis are the coolant distribution units, or CDUs. These are the powerful hearts of the liquid cooling ecosystem, pumping precisely conditioned coolant to the servers. They are far more than simple pumps. They are sophisticated industrial machines. A single high-capacity CDU can cost hundreds of thousands of dollars, yet it can only support a handful of high-density racks. An AI data hall requires dozens of them, causing capital expenditures to surge into the tens of millions for cooling infrastructure alone. The problem wasn't just cost, it was availability. The sudden massive demand for these specialized units overwhelmed the supply chain. By mid-2026, lead times for new CDUs stretched from weeks to over 9 months. A secondary market for high-pressure industrial plumbing, valves, pumps, and heat exchangers exploded, with desperate operators paying huge premiums. Even with an unlimited budget, supply became the absolute limiter. The mounting delays and spiraling expenses turned a technological challenge into a financial nightmare. The liquid failure point was no longer just an engineering problem. It had become a critical program risk, threatening the entire economic model of next-generation AI. Deployments were paused. Multi-billion-dollar data halls sat idle, waiting for a solution. The industry had to prove reliability before it could move forward. The companies that could solve this plumbing problem, the industrial giants like Vertiv, Eaton, and Schneider Electric, suddenly held the keys to the AI kingdom. They were no longer just suppliers, they were the gatekeepers. The world's most powerful AI chip isn't being stopped by software bugs or trade wars. It's being stopped by the laws of physics. For hyperscalers like Microsoft and Meta, this physical reality has a staggering financial consequence. They are sitting on billions of dollars in advanced silicon, entire fleets of Blackwell GPUs that they cannot fully deploy. The chips are in the building, but the power to cool them is not. This creates a crisis of idle capital, where the most valuable assets in the world are rendered inert, not by a lack of demand, but by a surplus of heat. The initial deployment schedules for Blackwell superpods, once aggressively slated for late 2025, began to slip. First into early 2026, then deeper into the year. The problem was systemic. Across their global portfolios, hyperscalers discovered that their existing data center infrastructure, designed for the previous generation of air-cooled hardware, was fundamentally incompatible with the thermal demands of the new architecture. The inability to reliably cool the 100-kilowatt NVL72 racks triggers the system's self-preservation mechanism, thermal throttling. The GPUs, sensing they are approaching their thermal limits, automatically reduce their clock speeds to generate less heat. This isn't a graceful degradation, it's a catastrophic failure to meet planned performance metrics. As a result, model training throughput falls precipitously below plan. A job projected to take 4 weeks now takes 6 or 8. For a 100,000 GPU cluster, this isn't just an inconvenience, it's a multi-million-dollar per day loss in computational output. The return on investment window, once measured in months, now slips quarter by quarter. This forces a painful recalculation. Corporate roadmaps are torn up and rewritten, no longer driven by chip availability, but by thermal risk mitigation. The critical path to AI dominance is no longer a silicon roadmap, it's a plumbing schematic. The only solution is a massive, invasive retrofit. This means cutting into the concrete slabs and raised floors of billion-dollar data centers to add the necessary high-capacity pipes. The plumbing required scales to industrial diameters, more akin to a chemical plant than a server farm. And the final, most crucial component, the plant-grade coolant distribution units, or CDUs, are the last to come online. Their procurement, installation, and commissioning becomes the single longest lead time item, defining the entire project timeline. The real winners of the AI race don't make chips, they make the plumbing. 2026 crowned new leaders in liquid cooling. Vertiv expanded capacity to address a multi-billion-dollar backlog. Eaton paid premium valuations to secure thermal capability. Schneider leveraged scale and multi-year contracts to lock demand. Their order books are full, influence growing. Markets rewarded control of the bottleneck. Custom cold plates, industrial-grade pumps, sophisticated CDUs, and loop control software. End-to-end systems, not commodity parts. Chip roadmaps push power and heat even higher. Demand persists for the next 24-36 months, minimum. These firms are the gatekeepers of deployment. The center of gravity moved from silicon to systems. Power in AI accrues to those who reject the heat. Contracts scale, backlogs extend, prices firm. Chapter 4 concluded. Blackwell is just the beginning. By 2027, the heat will double again. The Vera Rubin era points to 240 kilowatts per rack as a new waypoint. Cooling plant, plumbing, and validation must scale in lockstep. Beyond direct-to-chip, immersion may enter mainstream at scale. Treat cooling as a core competency, not a bolt-on. Subscribe to Vantage Point Media to track the industrial limits of AI. This is the thermal wall of 2026 and the blueprint to climate.